Why does cheese taste sharper and feel crumblier as it ages? The answer lies in the fascinating science of cheese aging, or affinage, a process where time transforms both the flavor and texture of cheese through a symphony of biological and chemical reactions. As cheese ages, enzymes from bacteria and molds slowly break down proteins, proteolysis, and fats, lipolysis, releasing a cascade of new compounds, amino acids, fatty acids, esters, and more that contribute to its evolving flavor profile. That mild, creamy cheese you started with, over months or even years, it can develop bold, nutty, sharp, or tangy notes, depending on the specific microbes and conditions involved. But what about the texture? Why does soft cheese become hard and smooth cheese turn grainy? During aging, moisture gradually evaporates and proteins reorganize into tighter networks. This results in firmer, more brittle structures. Crystals of tyrosine or calcium lactate may also form, adding a pleasant crunch in aged varieties like Parmesan. Analogy: it's like aging a fine wine or drying fruit. Time reduces water and concentrates complexity. Each cheese develops its own personality, shaped by temperature, humidity, microbial cultures, and the milk itself. The result is a culinary paradox: a single ingredient, milk, transformed into a spectrum of textures and flavors through nothing but time and microbes. How can a simple curd evolve over weeks or months into cheeses with nuanced flavors and distinct textures through a cascade of biochemical and physical processes? Cheese aging harnesses enzymes, microbes, and controlled environmental conditions to transform moisture content, protein networks, and lipid structures. Yet, subtle variations can yield remarkably different results. So far, so good, until we recognize that aging is not a uniform, predictable countdown, but a dynamic interplay of factors that inscribe memories of past conditions into the cheese. Early stages involve moisture loss and initial proteolysis by rennet and indigenous enzymes, setting the stage for texture development. However, slight shifts in temperature, humidity, or microbial succession can divert the maturation pathway, producing textures ranging from creamy and supple to crumbly and crystalline. At its core, two parallel biochemical processes drive flavor evolution: proteolysis and lipolysis. Proteolysis cleaves casein proteins into peptides and free amino acids, generating savory umami notes, bitterness or sweetness depending on the spectrum of released compounds. Lipolysis liberates fatty acids from milk triglycerides, which are precursors to aromatic ketones, lactones, and sulfur compounds that impart butyric, fruity, or rind-specific aroma. Meanwhile, salt and water diffuse through the curd, modulating enzyme activity and concentrating flavor molecules, transforming bland milk solids into complex taste profiles. Yet, even this mechanistic view conceals finer-scale intricacies. Microbial communities, surface molds, yeast, and bacteria colonize the rind and interior at different times, each species contributing unique enzymes and metabolites. For example, Penicillium camemberti on camembert surfaces generates ammonia that raises pH, softening the paste, while Ribibacterium linens on wash rind cheeses yields pungent sulfur compounds. These succession patterns are sensitive to microscopic fluctuations. A transient humidity spike may favor one species over another, rewriting the cheese's flavor trajectory. At even finer scales, physical processes and crystal formation add textural nuance. Tyrosine and calcium lactate crystals precipitate in aged cheddars and Swiss-style cheeses, giving a characteristic snap or crunch. The microstructure of the protein matrix, modulated by moisture gradients and enzymatic nicking, determines whether the cheese feels velvety, grainy, or brittle. Temperature oscillations influence water mobility and enzyme kinetics, so cellars with diurnal swings can produce cheeses with ripples of varying firmness or interior modeling. In essence, cheese aging is not a passive waiting period, but a richly orchestrated sequence where history matters. Each phase imprints chemical and physical signatures that steer subsequent transformations. Like other complex systems, from hysteretic materials to quantum fields, the final flavor and texture emerge from the intertwined legacies of environmental conditions, microbial choreography, and molecular interactions, making every wheel a singular testament to time. Cheese aging, or affinage, is the controlled maturation process that transforms fresh curd into a complex, flavorful product over time. During aging, biochemical reactions driven by enzymes and microbes progressively alter the cheese's protein and fat matrix. These transformations develop characteristic flavors, aromas, and textures that distinguish young cheeses from their aged counterparts. The rate and extent of these changes depend on factors such as temperature, humidity, and the specific microbial communities present. A young cheddar, aged for 2 months, tastes mild and has a firm yet pliable texture, whereas at 12 months, it develops sharp, nutty notes and a crumbly consistency. It is like fermenting tea leaves into pu'er. The longer latency unlocks deeper, more complex tastes and a thicker mouthfeel. Fresh cheese composition is dominated by intact casein networks and triglyceride-rich fat globules that yield a milky, neutral flavor. As aging proceeds, proteolysis and lipolysis break down caseins into peptides and free fatty acids, creating new taste and aroma compounds. These chemical modifications gradually overcome the base composition, generating sharpness, umami, and buttery or savory notes. Thus, the initial ingredient profile sets the stage, but aging defines the ultimate sensory character. In camembert, intact fats in young cheese give a greasy mouthfeel, while aged camembert releases ammonia and mushroom-like volatiles from protein breakdown. It is like endowing a plain canvas with layers of glaze and oil painting. The underlying paint remains, but the final image's depth and color complexity come from successive layers. At the molecular level, residual rennet and microbial proteases cleave casein micelles into smaller peptides and amino acids. This controlled breakdown softens the protein network, transitioning cheese from rubbery to creamy or crumbly textures depending on the rate of proteolysis. The distribution of these smaller protein fragments also influences water retention, thereby affecting firmness and spreadability. Overly aggressive proteolysis can lead to grainy or pasty textures if the network collapses too rapidly. Brie's silky, oozy interior results from rapid proteolysis near the rind, combined with slower breakdown in the core. It is like gradually untying the knots in a rope. As loops are released, the rope becomes more pliable until it nearly disintegrates. Lipolysis, the enzymatic hydrolysis of milk fat, releases free fatty acids that serve as precursors for esters, ketones, and lactones, key to cheese aroma. Different microbial lipases produce distinct fatty acid profiles, creating everything from buttery diacetyl in young dairy to pungent butyric acid in aged Parmesan. These volatiles can undergo further chemical reactions, such as oxidation or esterification, enriching the aromatic bouquet. The balance between proteolytic and lipolytic pathways determines whether a cheese tastes mild, savory, or intensely piquant. In blue cheeses, lipolysis generates methyl ketones responsible for their characteristic sharp, spicy notes. It is like unlocking hidden notes in a wine by allowing slow oxidation, which brings out nuanced fruit and nut aromas over months. Water content and pH critically influence enzyme activity and microbial growth during aging. Higher humidity preserves moisture, fostering softer textures and encouraging surface ripening bacteria, while drier conditions yield firmer, crumbly cheeses. As acidity increases from lactic acid production, protease activity can either intensify or diminish depending on the enzyme's pH optimum. Temperature fluctuations also modulate microbial succession and reaction kinetics, making precise control essential for consistent outcomes. Roquefort cheeses aged in damp caves maintain high moisture for creamy veins, whereas Granny Smith-style cheddars aged in drier cellars develop dense, granular interiors. It is like curing meats. Humidity and temperature vaults must be carefully managed to avoid spoilage while developing desired flavors and texture. Flavor compound concentrations often exhibit threshold effects, where initial slow accumulation yields minimal taste, but beyond a critical point, the aroma becomes intensely perceptible. Small additional increments in key volatiles can dramatically amplify perceived sharpness or creaminess. This nonlinear sensory response explains why cheeses aged slightly past optimal can suddenly taste overwhelmingly strong. Recognizing these thresholds allows affineurs to time the maturation precisely. A Gouda aged 18 months may taste mellow, but at 24-30 months, it abruptly acquires crystalline crunch and intense caramelized notes. It is like tuning a radio. A slight turn past a certain frequency brings a station in loud and clear, whereas nearer the threshold, it remains faint. Understanding aging's biochemical and physical effects enables cheesemakers to craft products tailored to consumer tastes, from mild table cheeses to robust grating varieties. By manipulating aging time and conditions, artisans create a spectrum of sensory experiences across a single milk source. For artisanal and industrial producers alike, controlling these variables is key to brand differentiation and market segmentation. Consumer preference studies often correlate perceived texture and flavor profiles with optimal aging windows. Manchego is marketed in tiers: fresco, 2 weeks; semi-curado, 3 to 6 months; and curado, 1+ year each offering distinct taste and texture. It is akin to vintners labeling wine as young or old to signal body and complexity to drinkers. Ensuring uniform aging across batches demands rigorous monitoring of microclimate, microbial populations, and chemical markers. Small variations in temperature or humidity can lead to off flavors, textural defects, or microbial overgrowth. Analytical techniques such as mass spectrometry for volatile profiling and rheometry for texture analysis are employed to detect deviations early. Despite technological advances, replicating the nuanced conditions of traditional caves or cellars remains challenging at scale. Large-scale cheddar producers use automated humidity and temperature-controlled rooms and regularly test for moisture, pH, and microbial counts to maintain consistency. It is like baking artisanal bread in industrial ovens while trying to replicate the unique steam and heat dynamics of a wood-fired hearth. Emerging sensor technologies and machine learning models promise real-time prediction and optimization of aging trajectories based on chemical and physical data streams. Novel affinity materials and bioengineering of starter cultures could accelerate or customize specific proteolytic and lipolytic pathways. Understanding the molecular details of aging may lead to synthetic or hybrid products replicating aged cheese profiles without long maturation times. Ultimately, deepening our insight into how aging affects cheese will enable both preservation of traditional methods and innovation in dairy science. Pilot studies use electronic noses combined with predictive algorithms to forecast optimal aging endpoints before overt sensory changes occur. It is like equipping a violin with sensors that alert the musician when the wood reaches its peak resonance for a given performance.